Okay, question 6. A sample of gas with a volume of 0.6 liters exerts a pressure of 0.46 atmospheres at 303 Kelvin. What pressure will the sample exert when it is compressed to 0.2 liters and cooled to 258 Kelvin? Okay, so with this one, this particular problem, we're given volume, pressure, and temperature. Okay, and then we're given changes in all three of those. So if we're given changes in volume, pressure, and temperature, we're using the combined gas law. So that's the law that combines Boyle's, Charles, and Gay-Lussac's laws, okay, together, because there's a change in all three properties, which is P1V1 over T1 equals P2 T2, or P2V2 over T2. Okay, so it asks what pressure will the sample exert when it is compressed. So these are your final. Okay, so we want to know what pressure. All right, so we're solving for P2 because we're looking for the final pressure. So in order to isolate P2 by itself, okay, I'm going to multiply by T2, which would get T2 off the bottom and take it to the other side, okay? So because we multiplied, T2 would go on top, and now I've got to get rid of V2. Well, because these are multiplying now, I'm going to divide by V2, which would cancel it here to leave P2 by itself. But then because I divided it on one side, I've got to divide it on the other. So V2 is going to go on the bottom over here. So to rewrite the equation, it should be temperature 2 times pressure 1 times volume 1 divided by volume 2 over temperature 1 is going to give you your pressure 2. Okay, so now I can just identify all these from the problem and plug them in here, and it'll give me pressure 2 since I don't know this. Okay, so my temperature 2 is here because this is my final temperature, and it is in Kelvin, so I don't have to do anything to it. So 258 kelvins. Okay, my pressure 1 is up here in ATM, or atmospheres. Okay, and then my volume 1 is 0.6 liters. Okay, all right, divided by my volume 2, which we said was 0.2 liters. All right, and then I'm multiplying that by temperature 1, which is 303 kelvins. Okay, we always want our temperature in kelvins, so kind of saves me some work there. So now I can just go ahead and plug this straight into my calculator. Okay, so 258 times 0.46 times 0.6. Okay, so that's the number from the top, and I'm going to divide that number by 0.2 times 303 from the bottom numbers. Okay, which is going to give me 1.175. I'm going to round that so that 5 kicks that 7 up to an 8. So what my final answer should be is that pressure 2 is equal to 1.18, and my first units of pressure were atmospheres, ATM. Okay, so ATM. Okay, and that's how you solve a problem using the combined gas law. Okay, question 7. A balloon filled with air has an internal pressure of 1.58 atmospheres and a volume of 1.56 liters. If the balloon is exposed to conditions where the pressure is 16.4 atmospheres and there is no temperature difference, what will the volume of the balloon be? Okay, so in my problem here, it gives me pressures, okay, and liters, which is a volume, and ask me what the volume would be. So I'm only comparing two things, which is volume and pressure. So comparing volume and pressure with no change in temperature is Boyle's law, which is P1V1 equals P2V2. Okay, so what will the volume of the balloon be? Well, so I'm solving for V2. So what I want to do is divide by P2 here in my original formula to get rid of it and take it to the other side. Okay, so in order to solve for volume 2, I just have to take my pressure 1 multiplied by my volume 1 and then divide by my final pressure. Okay, so P1 in this problem is 1.58 atm. Okay, and that's going to be times my volume 1, which we said was 1.56 liters. Okay, and I'm going to divide that by my pressure 2, which we said it would be, the balloon would be exposed to this pressure, this condition, 16.4 atmospheres. Okay, so all these numbers would give me what volume 2 equals. So if I plug that into the calculator, 1.58 times 1.56, all right, and then I'm going to divide that whole number by everything on bottom, 16.4. So round that to 2 decimals, so 0.15. Okay, so volume 2 equals 0.15, and the units of volume was liters here, so it has to be liters in my final answer. Okay, those units have to match, and that's how you would solve a problem using Boyle's gas law. Okay, so question 8. Our particles in a gas are far apart relative to their size. This property would explain which of the following? Well, this is part of your kinetic molecular theory. So because gas particles are so small and they're so far apart, it allows them to be highly compressible. So if I put them in a container and decrease that volume, okay, those particles have room in between the particles, and so they're able to be compressed, or to be put under more pressure. Okay, so it allows gases to be highly compressible because their particles are far apart. Unlike solids, what we discussed earlier this year, that solids are tightly compact together. Okay, they're kind of in a fixed position. There's not much room in between their particles. Gases are way different. Okay, and then question 9 says, if a temperature of gas is increased, what happens to the average kinetic energy of those molecules? Well, we know if we increase the temperature, those particles are going to begin moving faster and faster and faster, and so the kinetic energy is going to increase as well. Okay, so the average kinetic energy or motion of those gas particles is going to increase whenever the temperature increases. Okay, kinetic energy will decrease if temperature decreases. Okay, question 10. How many moles of helium gas are present in 14.8 liter sample at STP? Okay, so again, a little hint for your test. Whenever we see the moles, okay, we're dealing with the ideal gas law, which is PV equals nRT. Okay, so it wants to know how many moles. So again, we're solving for N. Okay, so just like in one of our previous problems that we've already done, I got to get N by itself. So I'm going to divide by RT. Okay, so that cancels it there. So PV over RT will give me the number of moles. All right, so now I just need to identify these. So my pressure, okay, And some of you get confused by this. You say, well, there's no pressure. Well, STP is a big hint. We know that at STP, I'm at 1 atmosphere. Okay, that's the pressure. And temperature is 0 degrees Celsius, or we know that's 273 kelvins, which kelvins is what we have to use in these, so we're going to use that number. All right, so pressure we said was 1 atmosphere, which is for ideal gas law, you have to be in atmospheres, times your volume, which has to be in liters, so it is in liters here, so 14.8, divided by R, which we know is a gas constant, which is 0.0821, times my temperature, which we said came from STP, so 273 Kelvin. All right, so we can plug it in to our calculator just like that. So 1 times 14.8, and then I got to divide that number by 0.0821 times 273. Okay, and notice how I put these in parentheses. What you don't want to do is not put these in parentheses, because then the calculator is going to calculate it as this number divided by that, and then calculate it and then times it by that number. Okay, you want the whole top to be divided by the number on bottom after these two have been multiplied together. So if you plug it in exactly like this into your calculator, it's always going to give you the right answer. Okay, so that gives you 0.660 moles, okay, because we were finding moles. I round that to 2 decimals. That 0 just leaves that 6 the same. So 0.66 moles because we were finding N. Okay, so that's using the ideal gas law to find your number of moles. Okay, I'm going to go ahead and skip number 11 for our review. It's using the ideal gas law there to solve. Okay, I want to look at number 12. Okay, so for number 12, again, what is the volume of 1.5 moles of O2 at STP? All right, so moles clue us in that I'm using ideal gas law, so PV equals nRT, and I'm trying to find volume. So I want volume by itself, so P and V are being multiplied, so I'm going to divide by P to get rid of it and take it to the other side. So the formula I'm really going to use here to solve for volume, which is what I'm looking for, is volume equals nRT divided by pressure. Okay, so now I can plug in everything. So N is the number of moles, which we said is 1.5 moles, times R, which we know is a gas constant, 0.0821, times temperature, which we said we're in STP. So we know in STP the temperature is 273 Kelvin, or 0 degrees Celsius, okay, but we have to be in Kelvin here, divided by your pressure, okay. We know at STP our pressure is 1 atmosphere, okay, and then in the ideal gas law, I've got to use atmospheres, ATM, okay. So once I have those numbers plugged in or put in like that, just plug them into the calculator. So 1.5 times 0.0821 times 273, and divide that number by 1, which really we know anything divided by 1 is itself. So round that number to 2 decimals, so that 9 is going to kick this 1 up to a 2. So we have our volume equals 33.6 0.62, which is what we got from the calculator. And volume has to be in liters in the ideal gas law. Okay, so we're in liters there for volume.